Hi everyone, for today's lesson we are going to be using technology with polynomials. Our learning objectives for today are for you to be able to say, I can use the graphing calculator to find the zeros, x-intercepts, local maximums, and local minimums. And I can model a situation using a polynomial function. So for today's lesson, you will need access to a graphing calculator. Please make sure that you have access to a graphing calculator before you get started with this lesson. Here we go. Here are the steps for identifying key points of a polynomial function. First of all, we are going to be working with our second trace feature. We're going to be working with our calculator, and we're going to be working with our second trace feature, which is our second trace if we want to calculate. We're going to be working with values, zero, minimums, maximums, intersections. I believe we've already worked with intersections. So it's primarily going to be second trace. We are also going to be working with regression as well. Before you get started with any of the problems that we are going to be working with, always make sure that your plots, if you press Y equals, make sure your plots are off. You don't want to have any of these highlighted. If they are highlighted, like something that you see here, all you need to do is press the up arrow. If it's blinking, press enter and it'll turn off because you don't want your plots to be on, not quite yet. For any of the points that we are going to be working with, we are going to need to move to the left of the point for what we call the left bound. Then we're going to press enter. Then we're going to move to the right of that point, trying to get as close to it as possible. Then we'll press enter. This will represent the right bound. And then we'll press enter again, because that will represent our guess. And what will happen is it will give you an ordered pair. So example number 1 says, use your graphing calculator to graph the function. Identify the x-intercepts and the points where the local maximums and local minimums occur. Round to the nearest thousandth if necessary. So what we have here is a quartic function. And what I want you to do is please go ahead and enter this function directly into your calculator. What you do is you press Y equals, and I'm going to put x raised to is this caret button over here located below clear. Raised to the 4th power, and I press the right arrow because my calculator will continue going into the exponent position, plus 3x raised to the 3rd power minus x squared minus 4x minus 5. Once you have your function entered into your calculator, the next thing you want to do is click Graph. And you want to make sure that your graph is something that you can see. Can you see all of the minimums and maximums? If it makes sense, you might want to change your window. I'm going to check out my window right now, and it looks like my X maximum is 20. I'm okay with it being 20, but it doesn't need to be that exactly. Maybe I'll make it to 10. So x minimum is negative 10, x maximum is positive 10, scale of 1 is fine. By looking at my minimum, it looks like my minimum is really, really close to the bottom, so I think I want to kind of view more of the y-axis going towards infinity. So I think I want my y minimum to be, instead of negative 10, I'm going to try negative 15 and have my maximum be 10 and keep my scale going by 1. And I'm going to look at what that graph looks like. Oh yes, so now everything looks like it's directly in the center, and I really like the way I have my scale set up. Your scale and my scale might be set up very differently, so I want you guys to just keep that in mind. Our scales might look different, and that is okay. All right, so now that I have my scale set up, I want to first identify x-intercepts. Remember, x-intercepts and zeros, they are related to each other. So we're going to press second trace, and we're going to go to where it says 0. That represents where your x-intercepts are. And what I'm going to do is I'm going to move my blinking bug, my cursor, to just to the left. I can't quite reach my x-intercept. So I'm going to go to the left. So notice my arrows. Here's to the right, here's to the left. I can't quite make it, so I'm going to call this my left bound, and I'm going to click enter. It's now going to ask you, is this your right bound? So I'm just going to press the right arrow one time, and that represents my right bound, and I'm going to press enter. It's going to ask, is that your guess? And I'm going to say, yes, it is. Enter. And now I end up with my first 0, and we typically round our answer, or this is asking us to round to the nearest thousandth. So I'm going to write negative 3.074, comma 0. That's my first x-intercept. When we always write x-intercepts as ordered pairs. Now I'm going to repeat the process because I have another 0 on the other side. Second trace, going down to 0, and I'm going to repeat this process. I'm going to press my arrow going all the way over until I reach my, so here's my left bound, here's my right bound, left, right. Here is my left bound. I'm going to press enter. My right bound is just above. I click enter, enter. And it looks like 1.4222 because that's a 7, so 1.4220. These represent my x-intercepts. Now we want to identify our local maximum. And in this problem, we have one local maximum. So I'm going to press second trace, and I'm going to go down to maximum. And I'm going to move my cursor until I get really, really close. And I'm going to analyze the y values. So I'm at negative 4.2, negative 3.67, negative 3.4, negative 6. Or 3.64. So I'm going back down again. So it looks like negative 3.46. This value looks like it's the highest. So I'm going to press enter. And I guess I'll go one to the right and press enter and then enter again. And it looks like I ended up with negative 0.638, comma, negative 3.468 is my local maximum. So some students have said to me, hey, Miss Olivero, I did not get the exact values you did when I did it in my calculator. So this is what I'm going to say to you. You've got to be really close, like no more than 100th off. You should be pretty close, and I will give you full credit if you are close. If you're off by more than 1/10, that means you didn't do it correctly. So you want to make sure that you are pretty close to my numbers. All right, let's go ahead and find our two local minimums. So we have two local minimums. So I'm going to press second trace. And I'm going to go to where it says minimum. And I'm going to move my cursor, really paying attention to my y values, because that's going to tell me once I've reached my minimum. So negative 8.6, negative 9.4, negative 9.5, negative 8.7. So it looks like I'm reaching like the smallest that I can right here at negative 9.57. And I'm going to press enter. And then I'm going to press the right arrow one time, enter, and then enter again. And it looks like negative 2.277, comma, negative 9.612 is my first local minimum. So now I'm going to repeat the process, and I'm going to go down to where it says minimum once again, and I'm going to move my cursor, really paying attention to my y values. So I'm at negative 5.8, negative 6.6, negative 7, negative 6. Okay, so my most minimum point was negative 7.01, and I'm going to press enter. I'm going to press the right arrow one time, enter, and then enter. And I ended up with my minimum being 0.676 and negative 7.025. And these are the values that I ended up getting. Once again, your values should be really, really close to mine, if not the same numbers. All right, let's go ahead and look at example letter B. For example letter B, I'm going to go back to y equals, and I'm going to enter this function directly into my calculator. So I have 0.5x to the third power plus x to the second power minus x plus 2. And once you have it entered into your calculator, we're going to press graph, and we're going to analyze our situation to make sure that we can see what's going on. And I can pretty clearly see what's going on, but I think I want to adjust my scale personally. I'm okay with x going from -10 to +10, but I don't think I need my minimum to be -15 anymore. I wouldn't mind making my minimum -5, but this time maybe making my maximum instead of 10, maybe making my maximum maybe 8 this time, and seeing what that does to the graph. Oh yes, I really like this because I can clearly see the behavior in my graph. So always be open to changing your screen so that you can, sometimes you might need to make the screen wider, sometimes you might need to narrow it. It just depends on what your needs are and the type of function that you have. So I'm going to press second trace, and I'm going to go down to 0, and I'm going to identify my x-intercept. And in this problem, I only have one x-intercept. And so I'm really going to pay attention to my y values. So here's my left bound, so 0.63. Oh, I didn't make it. So I'm going to call that value my left bound, enter. I'm going to press the right arrow one time, and now my cursor is above the x-axis, and I'm going to press enter. That's my guess, so I'm going to call enter again and end up with -3.074. Comma 0. That is my 0 of the function. Now I'm going to identify my local maximum, and in this problem I only have one local maximum. So I'm going to press second trace, and I'm going to go down to where it says maximum, and I'm going to press enter. I'm going to move my cursor, really paying attention to my y values. I'm at 3.4, 3.8, 4.0, 4.1, 4.0. So 4.1, I'm going to call that my left bound, enter. Press the right arrow one time, enter, enter. And it looks like my local maximum is located at -1.702, comma, 4.134. All right, let's go ahead and find our local minimum. I'm going to press second trace, and I'm going to go to where it says minimum, enter. And I'm going to move my cursor so that I get as close as I can. So it looks like I'm at y is equal to 2, 1.8, 1.7, 1.8. So 1.79 is my smallest value, and I'm going to press enter. The right arrow one time, enter, enter. And I ended up with 0.426, rounding it to the nearest thousand. So 255 means 426, comma 1.794. Cool, and that's how you identify local maximums and local minimums on your calculator. So now what we're going to do is we're going to apply this knowledge with a story problem. And it says, you are making a rectangular box out of a 12-inch by 15-inch piece of cardboard. The box will be formed by making the cuts shown in the diagram and folding up the sides. You want the box to have the greatest volume possible. So what we want to do first is we want to write a model to represent the volume of this box. So I really want you to think about what's happening here. So the volume of this box is going to be the area of the base times the height. And what I'm doing right here is I am emphasizing what the base is going to be. Because remember, all of these sides are going to be folded up. where the height is going to represent x. So if you can imagine that. Remember, if we're talking about volume of a box is length times width times height. We have to figure out what the length and the width of our base is multiplied by our height. So if you can imagine these pieces being folded up, if they're all the length of x, our height is going to be x. My length, well, think about it. It started off being 12, but then I'm folding up the sides and I'm losing x twice. Not just once, but I'm losing x twice. So it's really 12 minus 2x. That's what this length is. I've lost a little bit of x on each side of 12. And so that's actually what my length is, with my width being, well, one side, I'm losing an x on both sides of this 15. So that's going to be 15 minus 2x as well. So my volume, that's going to be my height, which we know is x, times my length, which we know is 12 minus 2x, times my width, which is 15 minus 2x. And I preferred to put x in the front just because that is the structure that we're normally used to. You could put x at the end. There's nothing wrong with that. Letter B says, what is the maximum volume? So think about this. This is a x, 12x minus 2, 12 minus 2x, 15 minus 2x. If we were to calculate the degrees, this is going to be a degree of 3, a cubic function, in which a cubic function doesn't exactly have a maximum because its domain and range is all real numbers. So what the maximum that they're talking about here is actually your local maximum. And more specifically, we are interested in the y part of that local maximum, because notice that v, our volume, is in the y position of the function. X, remember, represents just the height of the box. So what we're going to do is we're going to put this function directly into our calculator. And so I'm going to put into my calculator x times 12 minus 2x times 15 minus 2x. So putting this into my calculator, I'm going to press graph and see what kind of situation I'm in. Yikes, I am not seeing what I need to see. So I'm going to actually go to zoom and see if I can make it fit. Scrolling down to zoom fit, zoom 0. So click zoom and I'm going down to 0 and let's see what this ends up turning out to be. Oh, I do not like that at all. That did not work for me, but I can at least see more. They have the Y minimum being like 1100. I don't like that at all. So why don't we go ahead and see if we can adjust the scale? What if we made the Y minimum? It looks like I'm not looking at any real information taking place down below. So what if we just made the Y minimum like -10? And we made the Y maximum 400. Let's see how that changes things. Okay, so I can see a lot more of what's going on if I make the maximum 400. So I wonder what would happen if I adjusted my window again and made my Y minimum -100 just to see if that would help. And then make my scale go by tens to see if that expands out my shape. Okay, that looks a lot better. And I can maybe even adjust my my X scale so it's not a -10, maybe make it -5 and see what that looks like. Oh, I like that a lot. So sometimes it takes quite a bit for you to adjust your scale so that you can really see what is happening here in the function. And once again, we're just interested in that local maximum. So I'm going to press second trace and I'm going to go down to max. And I'm going to really pay attention to the Y coordinate. So I'm at 175, 176, 177, 176. So it looks like 177 was my highest value. And I'm going to press enter. And then a right arrow one time, enter and enter. And it looks like my maximum value ends up being, now remember, x represents the height. So this 2.2087, this represents what the height of the box would be. 177.2, if we rounded to the nearest tenth, is what the directions are asking us. That's 177.2. And this is volume. And remember that volume, it always is in units cubed. And so because we're talking about inches, our volume is going to be 177.2 inches cubed. All right, let's go on to the next question. Now it's asking, how long should you make the cuts? So let's go back to what that maximum was again. Hopefully it's right there. Let me go ahead and adjust my screen. Enter, enter, enter. So let me go back to that max again. I didn't mean to clear it out. And it looks like we should make our cuts, which is our x value, 2.2 inches. Because our ordered pair for the local maximum was 2.2, comma 177.2. So 2.2, this represents x, this represents our volume. So you should make the cuts .2 inches to maximize the volume. Letter D asks, what will the dimensions of the box now be? So we're looking at our height, which remember our height, that was equal to x. So that is going to be 2.2 inches. We have our length, which remember I called the length 12 minus 2x. So that's going to be 12 minus 2 times 2.2. So I'm going to put it in my calculator. 12 minus 2 times 2.2. And I end up with 7.6 inches. And my width, that is equal to 15 minus 2 times x. So minus 2 times 2. So I'm going to put 15 minus 2 times 2.2 in my calculator and end up with 10.6. 10.6 inches. And those are our dimensions. So when we are given a set of points, so now we're going to transition. This was modeling, and now we're going to be heading into regression. So when given a set of sets of points, we have in the past used the quadratic regression feature. We've also learned before about linear regression, especially is discussed in Algebra 1. So we talk about the regression feature in our calculator to find a model that fits the points. But what if the data doesn't suggest a quadratic model? If we know the type, meaning if it's cubic, quartic, quintic, etc., of higher order polynomial model we are looking for, the graphing calculator can also perform those types of regressions. It can perform a cubic regression, and it can also perform a quartic regression. So here are the steps for polynomial regressions using the graphing calculator. The first thing you want to do outside of entering data into your calculator is you want to make sure that you clear all lists or clear your RAM. And the way that you want to do that is you want to press second and then the plus sign. And you can either go, depends on what you want to do. So if I press second plus sign, if you want to go to clear all lists, that's 4 and then enter. And now it says done. So you can say 4 and then enter. Or you can clear your RAM by going second plus sign. For me, I have to go down to number 7 that says reset. Depending on your calculator, you might have to go to a different number. But reset, which is 7, all RAM, which is 1, and then yes, reset, which is number 2. Second plus sign 7, 1, 2. But regardless, you need to make sure that you clear your list before you get started with any of these regression problems. Then what you're going to do is you're going to enter your X values into list 1 and list 2. List 1 and list 2 are located in the stat button. You're literally going to press stat and then edit. So I'm going to write down those steps. You want to press stat and then edit. And then what you're going to see is L1 and L2. L1 represents your list of X values, and L2 will represent your list of Y values. And then we will do regression, but let's go ahead and get started with this example first. It says the table shows the average price in thousands of dollars, so that's going to be important, and thousands of dollars of a house in northeastern United States from 1987 to 1995. So T represents our year that we're talking about, and P represents the price. We want to find a cubic model for the data. We want to let X represent the number of years since 1987. So I want to warn you, don't use the number 1987, 1988, 1989. We don't use that. We want X to represent the number of years since 1987. Well, since 1987 is 1987, we're going to use the number 0. 1988 is 1 year since 1987. 89 is 2 years, 3 years, 4 years, 5 years, 6 years, 7 years, 8 years. So in your table for list 1, we are going to enter in our X values of 0, 1, 2, 3, 4, 5, 6, 7, and 8. Go back through and make sure that you entered in your data correctly. I always press enter or the down arrow as I'm going on to my next number. Next, we want to enter in all of our Y values. So our Y values in this case, we have 140, 149, 159.6, 159, 155.9, 169, 162.9, 169, and 180. You know you did it correctly when you go back through your ordered pairs and you verify that they match. Always verify that they match. That's really important. Many times I've even made mistakes because I didn't enter in the data correctly. So you want to be very, very diligent and tedious with making sure that those values are indeed accurate. So now what we want to do is we want to do a regression. So we're going to press stat once again, which stat is located below delete, and we're going to go over to calculate. From here, we want to go down. We have quadratic regression, cubic regression, quartic regression. But this one, because it's asking for a cubic model, we want to go to cubic regression. And we're going to press enter. This is where your calculator might vary. My calculator requires me to press enter 5 times. Some people's calculators don't require you to press enter at all. I'm sorry, just enter 1 time. It just depends on your calculator. So mine requires 5 times. And here is my model, my cubic model, and my A, B, C, and D values. We want to round our answers or our values to the nearest thousandth. So I'm going to write my values. So I have Y equals 0.242 T, I don't know why I said Y. This is actually P because I wanted my variables to be accurate. So this is P. Sorry about that, guys. P equals 0.242 t to the third power minus 2.995 t to the second power plus 13 point, looks like it's 454 t plus 139.767. There is my model. Now, assuming that this model continues to be accurate, we want to predict, because this is a model. Models are used for predictions. We want to predict the average price of a house in northeastern United States in 2000. And we want to show our work. So 2000, we're not going to let t equal 2000. We're talking about the number of years since 1987. So how many years are there between 1987 and 2000? That's 13. We're going to let t equal 13. So we're going to show that substitution. P equals 0.242 times 13 to the third power minus 2.995 times 13 to the second power plus 13.454 times 13 plus 139.767. Be very careful and make sure that you enter these values directly into your calculator exactly as you see it. I end up with 340.188. Don't leave your answer like this, though. Think about it. We want to round our answer to the nearest dollar, and the nearest dollar isn't $340. From the very beginning, we were talking about in thousands of dollars. So really, this is 340.188 times 1,000. And really, the answer is $340,188. That is the average price of a house in the year 2000 in northeastern United States. That is the end of today's lesson. If you have any questions over anything I just talked about, please feel free to email me. Otherwise, I hope you have a wonderful day.